Okay, I'm going to be trying to do this third lesson and the last video lesson of the week without the webcam, just to see if it uploads faster, and also because there's a lot of images that you really probably want to see this time, instead of my ugly mug. Uh, okay, so this lesson is going to be about the interactions of waves. If you haven't done lesson 2 and lesson 1 already, video lessons, please go back to them first before you continue on to this one. It's just a lot of vocabulary that you're probably going to want to know before starting this one up. And after you're done with this, please make sure that you do the Google form to make sure you understand what you know and you don't know. Okay, the objective of this. You want to be able to define and compare the interactions of waves in order to understand and describe the characteristics of sound and light energy. The ending of the objective has been the same the whole time for all these 3 lessons, but is where we're building it from. Right now from this lesson, you're trying to learn about the interactions themselves. Interaction, if I'm saying, hey, what is interaction between students? They could be talking, you could be playing, you could be tossing a ball to each other, any of those things, right? And so generally speaking, there's a bunch of different things that can happen with waves too, either between other waves or boundaries. So what do you think about that? What do you think will happen when 2 waves meet? Start by, I think you're drawing up all the possibilities. And I remind you to please use your guided notes. I'm not even going to go back to them at this point. You should know where to find them in the assignment itself. Or if you're not taking guided notes, just take them on paper. So what do you think could happen when 2 waves meet? Try and think of all the possibilities possible. Take maybe 5 minutes or so. Okay. Now, if you're coming back, hopefully you thought about not just transverse waves against transverse waves, but transverse waves against boundaries. Say a transverse wave hits a wall, right? It might be different than if a wave hits a wave, and then maybe a mechanical wave versus light. And there's a lot of different possibilities here for sure. And we're not going to go over all of them. We're just going to go over the ones that hopefully will lay the best foundation for understanding the core of what waves are and how they interact with each other. So just a quick vocab review. Amplitude is the distance between the crest or trough and the rest position or rest line. Wavelength is from a repeating point to another repeating point, so a crest to crest or a node to a node, trough to a trough, any of those things. Here's another look. I just wanted to show you like a more realistic look of what longitudinal waves look like. It's really hard to imagine what they really look like, but this is something like what sound would be as sound travels over air, say. Imagine each of these particles is microscopic air particles, right? Molecules of air. So when you're talking, or when I'm talking, my vocal cords are actually compressing parts of air together, and those parts are touching other parts. And it looks like those parts just travel right through, right? But remember, waves don't transfer matter, they transfer energy. So if you're taking a look at any one of these dots are actually just going back and forth, and they're not moving across, right? That's just energy. Say pick this dot down here. Here's another red dot, right? It goes back and forth, back and forth. As much as it looks like it's going all the way through, it's not. And the 2 important vocab terms for longitudinal waves, once again, are compression zones, and how long this is really the amplitude of this, how much energy it has, and the rarefactions, which are the stretched out areas in between. Transverse waves, once again, kind of look like this. This would be a really, really simplified way of looking at light. The length of that wave really being, if I were to freeze light, boom, the distance between one place where it touches a line to the same place exactly. So that could be crest to crest, trough to trough once again. But the idea is the up and down is the transverse, and moving out is the direction of that speed, or the wave speed. So for this one, it might be fun to actually experiment a little bit. Usually we do this in school. We have tubs of water, but maybe take a couple minutes, take like 10 minutes if you have it. Go fill up a sink or a bathtub and try and stop it up. Put something to keep the water in there so you're not just wasting water constantly. And try and see if you're creating a wave, if you create an up or down disturbance or a back and forth disturbance. You know how to do that at this point. My 2-year-old daughter does that all the time when she's taking a bath. can you bend the wave? How do you bend it? Can you destroy the wave? Can you make it bounce off of something? Can you have it change its direction without even touching it? Can you make it bigger without touching it, or even with touching that wave? Can you make it move faster? How do you do that? So try and keep those things in mind. Go experiment. And if somebody's asking why you're splashing around in the bathtub, just say, hey, I'm just doing some science here. Okay, at this point, I'm going to imagine you just did that, and you discovered that you can, in fact, do all of those things. And we're going to talk about which each of those things are, and even a couple others as well. So what interactions can waves undergo? What can waves do, basically? One, this is the one that everybody knows about already. They can reflect. If you're looking in a mirror, you're actually looking at a reflection, and that's not a small thing to say that light can bounce off of an object and then bounce off of it in the same exact angle that it came in on. It's pretty darn cool. Reflection happens when a wave bounces after hitting a barrier. So this angle coming in is called the angle of incidence. Like an incident, it came in, there's an incident, and it bounces back off in a similar angle from perpendicular to the surface itself. I'm going to say that one more time because it's a mouthful. It will bounce off at an angle that is similar to the angle it came in on when it's on a perpendicular from the surface it was from. So the angle between the ray that's coming in and the surface itself would also be similar to the angle between the ray coming out and the surface, if it's a flat surface. I mean, that basically makes a lot of sense, right? It's a big mouthful to say it bounces off at the same angle it comes in on. What gets kind of cool is when it's not a flat surface. It even makes it more interesting. So reflection, all types of waves can be reflected. Sound is reflected. It's been reflected by animals and developed for highly tuned systems in bats, which use ultrasonic, meaning above what we can hear, to image out prey. Sonar is basically our adaptation. I'm sorry, sonar is our adaptation of dolphins and many other, like beluga. There are plenty of animals that live under the water that use it. And it's interesting, light travels slower underwater, but sound actually travels much faster underwater than above the air. So sound, even though you think, oh, you can't hear anything underwater, you just don't have ears built for hearing things underwater. If you did, you'd be hearing it a lot more clearly, and the sound itself travels a lot more quickly, which is why it's such a tool that's used by a lot of animals in the animal kingdom. And light can be reflected anytime you're seeing light at all. You're actually seeing reflections of light coming off of it, unless you're like staring at a light itself or the sun, which don't do that. It's dumb. I can say it's dumb to stare at the sun, I think, at this point. You're not seeing a reflection when you're looking at the light itself being produced, but basically anything that's not producing its own light is a reflection. If you're looking at your computer right now, your computer is producing the light that you see, but you might even see a reflection of the light off of the screen if you see it clear as well. Refraction. This one here is this is often confused for reflection. It's not a typo. Refraction is the changing of direction of a wave when it changes speed as it travels from one material, what we call a medium, to another. Probably all have experience with this. If you ever see that water makes it, something look either magnified or like it's broken if you're looking at the top of it. If you get a pencil or a pen and fill up a glass of water right now, you can stick it in there and see, yeah, it just looks broken. And it's obviously not, right? You maybe get some money off your kid brother or sister. You say, hey, I can break a pencil without breaking it. And they're like, no, you can't. And I say, boom, science. But understanding why that happens is actually pretty darn confusing. So we'll start with light. Light changes direction because it changes speed as it travels from one medium, or say air to water, right? Air is a lot less dense than water is, and it's the density that will cause that change in speed. This can happen with sound as well, but it's one of the few times that you can really see light changing a lot. So for, say, the straw here, it's just weird to think about, right? The light is traveling off the straw into your eyes quicker than it is when it's coming through the glass. And in this case, also the glass itself being bent will change the direction of it, just like a lens would, but better probably from this angle. You'd see the light coming in and actually literally slows down because it's going through something that it doesn't want to go through, right? Light doesn't need something to travel through, so it travels most quickly through a vacuum or absence of anything or gas, and it slows down as it has to get through more stuff. It's like imagining like a track star running on a flat surface that's an asphalt surface, and then all of a sudden they're turning a corner and they hit some mud. They're going to change direction and slow down. It's basically the same thing happens to light. Diffraction. So diffraction is different than most of them. I think that's why they call it diffraction. It's bending. So this can happen with light. It's not as common, but definitely happens with sound and water waves, mechanical waves. Basically, if it's allowed to go through an opening, even if it's not an opening like a barrier on one side or two making a little slit, it will bend out and cause this kind of a diffraction pattern. That's really important for understanding how light works, even though in this kind of a situation, it's like I have no idea how that would make any sense for light. It's not worth explaining right now, but it was a huge important evidence for the idea that light is a wave because they saw this diffraction pattern once shooting light through a little slit. And light wouldn't do that if it wasn't a wave. People were thinking it was just a particle, like a photon. That's how it's kind of both. All right, I tried to explain it. Fair enough. You all experience this. If you were to say, turn around, right, and shout through the house, that sound would bend upstairs. It would go, or if you have it upstairs, or would go around the doorways, right? It bends. If it goes in a straight line only, or if it's a reflection, it would bounce around in straight lines, but sound is bendy. And honestly, the longer waves get, the longer the wavelength is of waves, even long wavelengths of light, like radio waves, the more bendy they get. That's why we use radio waves for telecommunications, like Wi-Fi, and it can bend its way all around the house, where if you had a router that you had to see to get the information from it, that would not really work if you were trying to go around a wall or would get your Wi-Fi and walk upstairs or walk into the bathroom to I don't even know. So this is why you can hear somebody talking in another room with an open door even though you can't see them. Cool. So we've learned that waves can bend, they can change direction and slow down, and they can just straight up bounce off of other things as well. So go try that out real quick. And just curious, does that diffraction change anything about the sound wave? Okay, light can be diffracted as well, like I said, it's just not as typical. Light can be bent around really massive objects out there. It's called gravitational lensing. Like something like this, you actually would see light here is light that's coming from behind this massive, massive, massive object, probably a galaxy with a very dense center. And it actually bends the light so that from one side, you wouldn't technically see it from Earth, but the light gets bent around the galaxy because of gravitational lensing. The same idea though, it's still diffraction. This is a much cooler way of seeing it. If you were to take your hand, and I would recommend nothing brighter than your phone's flashlight, and just kind of like create like a tiny little space in between and take a look directly at that light, you'll actually see the result of interference from diffraction. Because of the way it's bending, the light will interfere with itself, and you'll actually see a couple lines instead of just solid light like you would expect. Try it out.